Hello, this is the first lecture of this course on Ricci flow, and this is new for me to do this without an audience. I hope you see me well. The plan is that today I just give an outline of the course and introduce notation at the same time. Here at the back of the board I have some of the technical issues, so you can reach me by email under my university address. You can find material on the course on the internet on the University of Tübingen. For the participants from Tübingen University, I'm also in the process of setting up Microsoft Teams to post extra material, references for the course, in particular references to Ricci flow, and hopefully I will be able to set up a blog that contains information on the status of the course. The course will allow for exams at the end. It will be mostly oral exams. Please make an appointment with me in order to set up an oral exam at the end of the course. I will set up the lectures as small pieces of 45 minutes, post 2 such pieces of 45 minutes each week, and the lectures will then later on be available for a repeated viewing if you want to go back to these lectures. Also, I will try to set up using Microsoft Teams interactive sessions where you can ask questions maybe every 2 weeks or even every week for half an hour, maybe on Monday or Tuesday after the lecture, and then we can discuss aspects related to the lectures, or you may pose questions leading beyond the material presented in the course. Okay, so that's for me to start, and now we begin the course with an outline of the notation and some ideas of what we want to cover in the course. By the way, these are the blackboards here in Oberwolfach, and you can view this at the same time as an advertising to come to Oberwolfach at some stage. Of course, if you're here in the room, we would have 6 blackboards available, but then you wouldn't be able to read the writing on the board. We've tested this out, so I will always use just one board so you can hopefully see my writing. Okay, we start with a Riemannian manifold. So this is notation and introduction. So we will have Mn G is a smooth Riemannian manifold. And the metric G with components Gij in some coordinate system I and j between 1 and n. Then I denote the inverse of the metric by the upper indices, and this is also used then in the usual way to raise and lower indices. Then related to the metric, of course, there is the Levi-Civita connection. Giving us a covariant differentiation nabla, and with nabla associated is of course the Christoffel symbols gamma I, j, k in the usual way, 1/2 G upper IL times d dxj GLK plus ddxk GJL minus ddxl GJK. And once you have the Christoffel symbols, then you get covariant differentiation. And covariant differentiation, for example, for a net vector field X means that you have gradient I xj equals the coordinate derivative of xj corrected by the plus sign gamma j I k xk, or if you have a one form, then you get that the covariant derivative of this one form omega j is given by dd xi omega j minus gamma l I j omega l. And in particular, if you have a function f from Mn to R, then you have to distinguish between the differential, which is given by df dxi dxi, and the covariant derivative, gradient I of f, is g upper ij df dxj, and we can then also on the next board explain the Laplace operator. So the Laplacian of f is the divergence of the gradient of x. So this is then also written as di of f, and this can be written in turn as g upper ij times the Hessian of f, and here with these lower indices, of course, this leads to g upper ij times the coordinate derivatives of x minus the Christoffel symbols times the first derivative. Okay? Now, the other notation I need is that the metric can be used to define a norm on tensors. So if T, say, for example, is a tensor with two indices, Tij, then we write for the norm T squared with respect to the metric G, G upper IL, G upper JK times Tij T LK. So we have a covariant derivative, we have a norm on tensors in a natural way with the metric G. The next structure we need is, of course, the Riemann curvature tensor. And here, let me start very classical with the coordinate way. we have the Christoffel symbols, and once we have the Christoffel symbols, we can compute the components of the Riemann tensor, and traditionally we first write the Riemann tensor with one index up and the others down. So the Riemann tensor with one index up is given by the derivatives of the Christoffel symbols. So this is equal, let me put a k here, and then this is ddxi of gamma hjk minus ddxj of gamma hik plus square terms gamma h ip gamma p jk minus gamma h jp gamma p ik, and of course you could define this much more abstractly, which you find in any book, but for computations it is useful to have these explicit formulas in a coordinate system. And the way to think of the Riemann tensor is that on the one hand you can view the Riemann tensor, of course, as a four-linear mapping from the tangent space with these four components into R, but because of the symmetries of these tensors, there's another way of looking at it which is important. So let's state the symmetries. The key symmetries are that it's antisymmetric in the first two indices, and also antisymmetric in the last two indices, and symmetric in the pairs ij and kl. And finally, another symmetry is the Bianchi identity, the first Bianchi identity, saying that if you take any three indices and rotate them cyclically, you get 0. So for example, the first three, jki l plus r j rki j l is equal to 0. And now, because of this symmetry here and the antisymmetry in the first two indices, you can also view the Riemann tensor as an operator from two forms at some point, mapping it into two forms again. Namely, you take omega ij and map it into r ij kl omega pq gkp glq. Because of the antisymmetry and the symmetry in these pairs, this is a symmetric operator with real eigenvalues. And this is often called the Riemann curvature operator. Okay. Once you have this Riemann curvature operator, you can form other structures from it. For example, you can look at certain components in certain directions because of this antisymmetry. For example, it makes sense to insert two directions and look at the curvature and direction of a two-plane. This will lead us to the sectional curvatures in a moment. And you can trace traces. So in the next step, we examine the traces and sectional curvatures, and this will lead us to the Ricci curvature, which we need for the Ricci flow. To do the computation, it's often useful to introduce an orthonormal denotation in orthonormal frames. To say what is sectional curvatures, let E1 be a local orthonormal frame, then we set sigma ik equal to rik ik, and call this the sectional curvature in direction of the plane the two-plane EIK, which is the span of EI and EK. Now, the sectional curvature, for example, on the sphere of radius r, we have that all the sigma ik are equal to plus 1 on r if I is different from k, and we have on hyperbolic space sigma ik is equal to minus 1 on r. Sorry, 1 on r squared, I should say. If I is different from k. Okay. Now, the Ricci curvature is then the trace of the Riemann tensor. Ricci curvature, I don't know Ricci, and put it's a symmetric tensor, and the components are given by the trace of the Riemann tensor. Okay. And finally, we need the scalar curvature, which is the trace of the Ricci curvature. R is G I K R I K, the trace of the Ricci curvature. The significance of the curvature tensor comes from the fact that you use it in order to compute the exchange of the second derivatives of a tensor, which of course you could also use as a definition. So here the significance of curvature. Comes from the fact, I have to get my indices right, that you can take a vector field xh, say, and commute the first two derivatives, and then what you get is curvature I, j, k, x, k, which of course is the same as g, h, l times r, I, j. And here we have to be careful about the order of the indices. That's the first formula. And when you exchange the second derivatives of a lower index, then you get R, I, J, K, L times G, L, M times omega N. So this is the key relation that you need for computations, and in particular when you apply this to the differential of a function, this is leads to the important formula that the Laplacian of the gradient of a function is the same as the gradient of the Laplacian of a function plus, and since you're here exchanging third derivatives, you get the Riemann tensor multiplied with the first derivatives of f, but because the Laplacian is the trace, you get the trace of the Riemann tensor, which is the Ricci curvature, so you get R I k times gradient k of f. So this is one important formula that is used very often. Now, the other important thing that I did not yet tell you about the Riemann tensor is the extra symmetry that you have between the first derivatives of the Riemann tensor, and this is the so-called second Bianchi identity. Will play an important role. Namely, it is true that the cyclic permutation of three indices of the first derivatives of the Riemann tensor, so J, L, K, J, K, L, M, plus gradient J, R, K, I, L, M, plus gradient K, R, I, J, L, M is equal to 0. And then you can contract this identity once and a second time. If you contract it once, you get that gradient I of the Ricci tensor JL plus minus gradient J R I L, because if you contract over K and M here, you get a minus sign, and then you get a plus sign gradient K R I K equal to 0. No, sorry, this is getting ahead of myself. Gradient K R I J L K is equal to 0. And then you can contract one more time. And if you do this, you get here gradient I of Rij. And for the next term, you get gradient J of the scalar curvature, which is the trace of the Ricci tensor. And then you get from here the trace of gradient Krik equals 0. And then you notice, of course, that the first and the third term are the same, and you get the important relation, which is called the second contracted Bianchi identity, which tells you that the divergence of the Ricci tensor is equal to 1/2 the gradient of the scalar curvature. This is the contracted second Bianchi identity. And now you have really all the tools that are needed in order to do computation with the Riemann tensor and do any computations in terms of curvature. Now, I wrote significance of curvature and gave you the first key significance as the exchange of second derivatives of tensors. Now, there's another way to think of the Riemann curvature tensor, which is important for the intuition, and that is that the Riemann tensor is telling you how much locally the metric deviates from the flat metric. So when you have normal coordinates at some point of the manifold, then very close to this point where you have the normal coordinates, it looks like Euclidean space, if it's a smooth Riemannian manifold. And normal coordinates means that you can even make the first derivatives of the metric 0, so it looks up to first order, like Euclidean space. But you cannot make the second order deviation from Euclidean space go away. And this obstruction of removing that second order deviation, that's exactly the Riemann curvature tensor. In other words, the Riemann curvature tensor is the one thing that shows up if you write out a Taylor expansion of the metric in a normal coordinate system. And let me just state this result. So Taylor expansion of Gij in normal coordinates as xi at P in a Riemannian manifold. You get the formula that Gij at x is given by delta ij, and then we know from normal coordinates that the next term is going to be 0. There's no derivatives of the metric, but then the term that comes next is minus 1/3 r I k j l times xk xl plus terms of order x cubed. And this can be easily computed by differentiating the exponential map twice at P. So differentiate the exponential map. And of course, once you have this Taylor expansion, it also tells you an expansion, for example, for the volume element near a point, and other useful information, and it helps you to get the right intuition about what the Riemann curvature is doing to the manifold locally. Now, having all these structures, it turns out that it is useful to decompose the Riemann tensor into its irreducible parts, because the vanishing of one or two of these irreducible parts gives a restriction in the Riemannian manifold that makes it special and gives us the first important examples. So let me talk about the decomposition of the Riemann tensor. Now, it's well known from algebra that a tensor like the Riemann tensor can be decomposed into orthogonal components with respect to the orthonormal group, that by looking at the symmetries you've already looked at, and by looking at the traces. So the decomposition of the Riemann tensor will rely on the examination of its trace parts. So in the first step, we take the Ricci tensor and decompose it into its trace part. So define the traceless Ricci and I call this Ricci with a 0 on top, which is with components R0ij, by setting R0ij to be Rij minus 1 on n R times Gij. Now, as you see, this is trace free because this trace is R, the trace of Gij is n. And then, of course, if you multiply this with this thing here, with the metric times some multiple, then you get 0. So we can write that Ricci itself is decomposed in an orthogonal way with the tensor 1 on n R times Gij. And the Ricci tensor squared, the norm of the tensor, can therefore be decomposed into two positive terms, the trace-free part squared, plus the norm of the trace part. The norm of the trace part gives me a 1 on n squared r squared, but this length is n, so I get 1 on n times r squared. Which means, in particular, that the norm of the Ricci tensor squared is bigger than 1 on n r squared. Like for any symmetric matrix, the norm squared is bigger than 1 on n times the trace squared, with equality if and only if the trace-free part vanishes. Now, once I have this trace-free part, it's clear that these two things are special components already at the level of symmetric two tensors, so they must play a special role in terms of the Riemann tensor. So we define the corresponding tensor having the symmetries of the Riemann tensor generated from this R and generated from the traceless Ricci. So in the second step, we define the tensor U with components Ui, J, K, L to be the tensor 1 over n times n minus 1 times the scalar curvature times Gik Gjl minus Gil Gjk. You can think of this as a tensor which is the identity as a map from the antisymmetric two forms to themselves. It certainly has exactly the same symmetries as the Riemann tensor itself. And similarly, we define V, Vijkl, as that part of the Riemann tensor which comes from the trace-free Ricci tensor. So this is 1 over n minus 2 times the trace-free Ricci tensor Ik Gjl minus R0 Il Gjk minus R0 Jk Gil plus R0 Jl Gik. Sometimes this is also written as 1 over n minus 2 times traceless Ricci wedge the metric, and we call this the trace-free Ricci part. And we call this the scalar curvature part. They are obviously orthogonal to each other because multiplying with U always means taking traces. But this guy here has as only trace the trace-free Ricci, and if you take another trace of the trace-free Ricci, you get trace 0. So yeah, let's state this here. So the trace of U, Gjl of U, I, J, K, L, of course, turns out to be the trace part of the Ricci tensor. And the trace part of Vijkl turns out to be the trace-free Ricci tensor. So once we have made these definitions, it is clear that the full Riemann tensor can be decomposed into this part plus the V part plus the rest. So altogether we have that the Riemann tensor can be decomposed as U plus V plus W, where W is the rest, and it's completely trace-free. There's no trace in W whatsoever, and actually this tensor W is called the Weil tensor, in honor of the mathematical physicist Hermann Weil. And this Weil tensor plays a crucial role in mathematical physics because you can do a computation that shows that this Weil tensor is conformally invariant. So it's a fact that the Weil tensor is conformally invariant in the following sense, that if you have a metric G hat, which is equal to lambda squared times G, and lambda is a positive function from n to r, then W hat ijkl is equal to lambda squared Wijkl. Notice the scaling, because the indices are all down. This doesn't, with the indices all down, doesn't scale like curvature. It really scales like lambda squared if G's hat is scaling with lambda squared here. Now that's just a fact about the Weil tensor, but it's important to notice its key decomposition. So now let me look at the time. I want to make these lectures roughly 45 minutes each, so maybe I conclude with a few remarks on the decomposition, in particular the two-dimensional and the three-dimensional case. Remarks. First remark is about n equals 2. Now in the case that n equals 2, there are so many symmetries, you can see that since there's only I, j can only be 1 and 2, it means that the only component of the Riemann tensor that survives are the component R1, 2, 1, 2, with all its changes. So this could be also minus R1, 2, 2, 1, and which is the same. Yeah. These are the only ones that are surviving. The only ones that are non-zero. So from these symmetries you can easily see that both W and V in this case are identically zero. The only term that survives is the tensor U, and U is equal to 1 on n minus 1 divided by n minus 2. So this is 1 over 2 times R times G1, 1, G2, 2 minus G1, 2 squared. And this is just the Gauss curvature. So in the two-dimensional case, the Gauss curvature is the only curvature that survives, and the Gauss curvature is exactly 1/2 times the scalar curvature, and the Ricci curvature in the two-dimensional case, Ricci Ij, then is simply the Gauss curvature times Gij. So you have a very simple structure in this case. Now, the more interesting case, well, the two-dimensional case is of course in itself extremely interesting, but not at this algebraic level. The more interesting case is the three-dimensional case. And it's a simple exercise that the condition on the symmetries of the Weil tensor plus the fact that the Weil tensor is trace-free. A simple calculation of how many possibilities there are, you have just I, J, K, all these indices can be just 1, 2, or 3. This shows you that in the three-dimensional case there's just not enough room to have a trace-free tensor with all these symmetries. So W has to be identically 0 in the three-dimensional case. But this means in turn that in the three-dimensional case you can completely express the Riemann tensor in terms of the Ricci tensor. So we get that Rijkl can be written as 1 over n minus 2 times this trace-free part, I write it down again, of the Ricci tensor R0jk GIL plus R0jl GIK plus 1 over n, well, and n in this case is 3, so we have a 1 here, and then n times 1 over n times n minus 1, which is 1 over 6 times the scalar curvature times GIK GJL minus GIL GJK. So the whole Riemann tensor is determined by this much simpler symmetric bilinear form given by the Ricci curvature. And now, since it's symmetric, it has 3 eigenvalues, and so the 3 eigenvalues of Ricci we may denote by lambda 1 and lambda 2 and lambda 3. So, for example, lambda 1 might be R11 in an appropriate coordinate system, so on. And then the Ricci curvature in this coordinate system would just be sigma 1, 2 plus sigma 1, 3, where these are the sectional curvatures. And lambda 2, similarly, in such a coordinate system would be sigma 2, 1 plus sigma 2, 3, and finally lambda 3 would be R3, 3 equal to sigma 1, 3 plus sigma 2, 3. And this gives us a relation that allows us to compute the eigenvalues of the Ricci tensor in terms of the sectional curvature, but it also allows us to compute the sectional curvatures in terms of the Ricci eigenvalues. For example, we get sigma 1, 2 is 1/2 lambda 1 plus lambda 2 minus lambda 3, and so on, cyclically rotate this through, and this gives you the corresponding expressions for the sectional curvatures sigma 1, 3 and sigma 2, 3. Maybe this is a good point to stop, and let's start in the next lecture with Ricci flow. Thank you.